required fail-safe action of the valve. But obtaining other information may require some research. You'll need information regarding the properties of the process fluid as it will exist at the valve inlet. This includes chemical properties of the fluid, which may influence final valve selection. In addition to the chemical makeup of the fluid, the physical properties of the stream also need to be established. Sizing calculations require information such as fluid pressure, temperature, density, and viscosity, to name just a few. Other information needed includes the minimum and maximum steady-state controlled flow, and the maximum flow rate that will be required to recover from a process disturbance. If the fluid is a slurry, it's also necessary to determine the weight percent and volume percent of the solids. You'll also want to know the size of the largest particles, as well as their hardness. Clearly, these factors influence valve sizing and selection. Properties of the process fluid aren't the only concern when selecting a valve. It's important to gather information about the piping system. One reason is that the control valve must conform to the applicable piping code. It's also necessary to ensure physical compatibility between the system piping and the valve, so you need the piping specifications. For example, do the specifications call for flanged, welded, or threaded joints? Are the pipes to be lined or unlined? This type of information is necessary to avoid costly discrepancies that may not be discovered until it's time to install the valve. Piping configuration is another factor that needs to be investigated. As you'll recall, configuration can influence the effective C sub V of a valve. Being aware of these influences is necessary to make a proper valve selection. The environment where the valve will be installed can also have an impact on valve selection. As you may recall, the classification of the area for electrical hazards is one important factor when making a selection. Other factors include climatic conditions, such as temperature extremes, atmospheric contamination, such as corrosive dusts and vapors, the seismic zone classification, and any unusual plant procedures such as washdown or decontamination. It's important while gathering data to keep in mind that non-technical factors such as budget constraints and delivery schedules are also elements in making a proper selection. Finally, it's important to get the opinion of the people that operate and maintain the valves. If they don't believe a valve will work, chances are it won't. As data is collected, it should be organized on a form such as this. This type of document will not only help with sizing and selecting, but it may also serve as a historical record of the basis for the valve's selection. This will prove useful if, for example, the process is to be revamped in the future. With all the data gathered and organized, a preliminary valve selection can be made. Unfortunately, there is no formula that can be used to identify the ideal control valve for any application. Instead, a list of potentially suitable control valves must undergo a process of elimination, where unsuitable valves are rejected. Consider this system, where the process fluid is a liquid that contains erosive fines. Steady-state operational conditions result in differential pressures of up to 150 psi. As you can see, globe valves with these trim styles do not meet the system requirements, and therefore they need to be eliminated from the list of suitable valves. Other charts and tables for various valve characteristics exist in this book and similar publications that will help in making a proper selection. Eventually, the list will be narrowed to a few valves. At that time, if all other factors are equal, cost may become a consideration, as well as personal judgment and experience. Now, the preliminary selection made frequently remains as the final choice. However, there are times when the sizing calculations reveal a more suitable selection. These calculations will be covered in the next segment, but for now, stop the tape. After making a preliminary valve selection, it's necessary to determine the size of valve needed and to verify that the valve won't be subject to excessive cavitation or flashing. The importance of correctly sizing a control valve cannot be overstated. For example, if this valve were significantly undersized, process operation would be restricted to low flow rates only. And increasing differential pressure to obtain higher flow rates could result in excessive noise, cavitation, and flashing. Of course, if the valve were significantly oversized, other problems might occur. The valve may be unable to control properly at small flow rates, thus limiting system turndown. System turndown is the ratio between the normal maximum flow and the minimum controllable flow. There would also be a general reduction in the quality of process control. So you can see, even if there is uncertainty in some of the data that's been obtained, it's important not to become too conservative when sizing the valve. Now, to begin sizing, you'll need your data sheet and some reference materials such as the ISA Handbook of Control Valves. Manufacturer's literature for the valve type that's been selected should also be handy. These references contain data that's needed for the calculations. They also include the formulas you'll need, as well as explanations. Now, let's take a look at a sample problem. The control valve we'll be sizing is to be used in a river water system that provides cooling for a process. Data that's been collected indicates that the valve will be located in an 8-inch Schedule 30 pipe. The maximum flow rate to the process will be 1,600 gallons per minute. Upstream pressure will be 42.6 psia, and downstream pressure will be 34.7 psia. So differential pressure across the valve is 7.9 psi. The preliminary valve selection is a butterfly valve with a 60-degree opening. Some of the factors that influenced this decision were the high flow rate coupled with a relatively low differential pressure. Now, the objective of sizing this valve is to determine the smallest valve size that will provide suitable performance. Past experience indicates that it may be possible to use a 6-inch valve in this service. The first step is to determine the minimum required flow coefficient. As you may recall, the basic flow rate equation provides a relationship between C sub V and some of our known data. Because we're interested in placing a 6-inch valve in an 8-inch pipe, we need to include the piping geometry factor, F sub P, in the equation. Now, it may be helpful at this point to think of the term F sub P C sub V as the effective flow coefficient for the installation. By rearranging the formula, a value can be calculated for this term. As you can see, for the valve to function adequately, the minimum required effective flow coefficient is 569. The next step, then, is to determine the actual effective flow coefficient for our valve choice when installed in this system. We do this by calculating a value for the actual F sub P and the actual C sub V. Let's do C sub V first. This is the equation used to calculate C sub V, where D is the diameter of the valve inlet and C sub D is the relative capacity factor for the valve. We know the diameter of the valve inlet is 6 inches. The relative capacity factor is available in reference tables, such as this. As you can see, the value of C sub D for a 60-degree butterfly valve is 17. Substituting values into the equation yields a value of C sub V equal to 612. Next, a value for the actual value of F sub P needs to be determined. This formula may be used. Since we already know that C sub D is equal to 17, the only unknown in this equation is sigma k. Sigma k is the sum of the k factors, or velocity head coefficients, associated with the inlet and outlet fittings in our installation. The factors k1 and k2 can be approximated by using these two formulas. Factors kb1 and kb2, the Bernoulli coefficients, are associated with the valve inlet and outlet respectively. Each can be found with this formula by using the appropriate valve size and pipe diameter. Note that if the inlet and outlet pipes are the same size, as in our case, these two factors are equal and they cancel each other out. It's common practice in fluid mechanics to use beta as a notation for the ratio between the valve connection diameter and pipe diameter. We'll use beta to simplify the formulas for K1 and K2. So, after solving for beta, we'll be able to work back through these equations to find the actual value of F sub P. Beta is simply equal to the valve connection size, 6 inches, divided by the pipe size, 8 inches, or 0.75. Substituting this value in the formulas for K1 and K2, we find they are approximately equal to 0.10 and 0.19 respectively. So sigma K is equal to 0.29. This value can be placed in the equation for F sub P. Working through the math shows that the piping geometry factor for our installation is 0.96. Finding the effective flow coefficient for the installation is now simply a matter of multiplying the two factors. Because the result, 588, is greater than the minimum required, 569, the 6-inch butterfly valve is a suitable choice for this installation. However, it's still necessary to determine if the installation will be subject to problems, such as cavitation. We'll look at one method that may be used to estimate when cavitation will occur. This method relies on the use of an experimentally determined cavitation index, K sub C, that is available for many valve styles. The published value for our valve is 0.3. This is the formula we'll be using. As you can see, the pressure of the fluid at the valve inlet, the vapor pressure of the fluid, and the cavitation index are used to calculate a differential pressure. This is an estimate of the differential pressure across the valve at which cavitation will begin. We already know the values of the cavitation index and upstream pressure. Vapor pressure for water at various temperatures can be found in a set of steam tables. The temperature of interest is the highest water temperature that will occur at the valve inlet. In our case, 90 degrees. The vapor pressure for 90-degree water is approximately 0.7 psia. Substituting these values into the equation, we find that when differential pressure across this valve reaches about 12.6 psi, cavitation will begin. Because the expected differential pressure across the valve is only 7.9 psi, cavitation should not normally occur. There are instances when the cavitation index is either not available or not valid. When this is the case, different formulas must be used to predict when cavitation will occur. These formulas are detailed in your text. The procedures illustrated in this segment are for ordinary liquid flow applications. The calculations used assume that turbulent flow exists. If the flow is not turbulent, or if the liquid is non-Newtonian in nature, other methods may apply. Your text provides additional material on these topics. In the next segment, we're going to cover valve sizing for gas and vapor flow applications. But for now, we're going to look at valve sizing for gas and vapor applications. As you'll see, the method used is very similar to sizing a valve for a liquid flow. The first step is to determine the required F sub P, C sub V for the application. And the second step is to calculate the actual value of the term. Then a comparison of the two values will indicate whether or not the valve is suitable for the application. For liquid flow, this was the basic working equation used. As you may recall, the development of this equation was based on flow of an incompressible fluid. However, gases and vapors are compressible fluids. As a result, a variety of correction factors are needed in the basic equation. Let's take a look at these factors, starting with the expansion factor, Y. Remember that As fluid passes through a restriction, pressure drops and fluid velocity increases. If the fluid is compressible, this reduction in pressure will result in a corresponding expansion of the gas or vapor. When a fluid expands, its specific weight decreases, so it follows that the specific weight of a gas must decrease as it flows through the restriction to the vena contracta. This means that the velocity of a compressible fluid must increase even more than it would for an equal mass of liquid. And because of the loss in pressure head, the fluid velocity downstream of the restriction must be greater than it is upstream. The expansion factor, y, is used to correct for these effects. The value of y can be determined by solving this equation. Now, as you can see, this requires values for 3 other factors, so let's take a look at them. X is the pressure drop factor. It's the ratio between the differential pressure across the valve and the valve inlet pressure. Flow through the valve will increase with increasing values of X. This ratio is also important to the flow of compressible fluids because the point at which flow through a valve becomes choked is a function of its value. X sub t is the terminal or limiting value of X. Values of X greater than X sub t do not result in any increase in flow. So this is the largest value of X that can be used in our equations. Values for X sub t can be found in a variety of reference charts. These values have been determined in the laboratory using air as the test medium. As you may suspect, the effective value of X sub t for a valve will be affected if the process fluid has different properties than air, or if piping geometry is changed by using reducers with the valve. To compensate for changes that are introduced by the use of inlet piping reducers, this formula must be solved. Outlet reducers do not affect the value of X sub t. When inlet piping reducers are used, the modified value of X sub t becomes this factor, X sub Tp. As you can see, this factor is also used to determine the value of y. This term, F sub k, is used to correct for process fluids with thermodynamic properties that are different from air. F sub k is the ratio of specific heats factor. It compares the ratio of specific heats of air, which is 1.4, to the ratio of specific heats for the process fluid, K. Finally, you need to be aware that y is limited to a range of values between 1 and 0.67. Values less than 0.67 result in choked flow and should not be used. Values greater than 1 are not possible. Now that you're familiar with the expansion factor, let's go back to the general flow equation. You can see that in addition to the expansion factor, the pressure drop ratio also appears in the equation. Remember, the value of this term is limited to X sub t and must be corrected when dealing with a process fluid other than air. Other new terms include the compressibility factor, Z. It's used to correct for the difference in behavior between real gases and ideal gases. Values for Z can be computed with this equation or can be found on compressibility charts. This factor is the absolute temperature of the fluid at the valve inlet, expressed in degrees Rankine. Of course, the temperature on the Rankine scale is equal to the temperature on the Fahrenheit scale plus 460. This particular form of the flow equation contains conversion factors so that the flow rate, Q, is expressed in units of standard cubic feet per hour. Other forms of the equation, providing for other units, are given in your text. Now that you're familiar with all the factors in this equation, let's work through a valve sizing problem. Our application involves a natural gas main. This is the data that's been collected for the installation. The first step is to determine the required F sub P C sub V. If you would like to take the opportunity to solve this problem by yourself, pause the tape when you hear the tone. After you have determined a value for this term, restart the tape. If you found the value of this term to be $13.99, you're right. Now, let's review how this value was obtained. First, the equation is rearranged to isolate the term F sub P C sub V. Then, known values are substituted into the equation. Values for Q, G, and Z can be directly transferred. Pressure and temperature values must be converted to absolute units. P1 is 15 psig, which is equal to 29.7 psia. And fluid temperature is 60 degrees Fahrenheit, which is equal to 520 degrees Rankine. When these values are placed in the equation, the only unknowns remaining are the expansion factor and the pressure drop factor. Now, you'll recall that X is used to calculate Y, so we'll determine its value first. X is found by solving this equation. It requires converting the value of P2 to an absolute pressure. By using a conversion factor and adding 14.7 to the result, P2 is found to be 15.1 psia, so X is equal to 0.49. It's necessary to recall that the value of X is limited by the value of X sub T, in this case 0.38. So this is the value used. You may also recall that the value of X sub T was determined experimentally. When fluids other than air are used, X sub T must be modified by F sub K, the ratio of specific heats factor. Now, for natural gas, F sub K is equal to 0.9, so the value of X to be used is the product of F sub K times X sub T, or 0.34. The only remaining value to be found is Y. All of the terms required to solve for Y are known, with the exception of X sub Tp. Since no reducers are used at the valve inlet, its value is equal to X. So the calculated value of Y is 0.63. This is less than the limiting value of Y, so the limit, 0.67, is used. With all of the terms known, F sub P C sub V can be calculated. The result is a required value of 1,399. The next step is to calculate the actual value of F sub P C sub V. The formulas used to calculate these values are the same as those used for liquid flow. Substituting known values into the equation for C sub V, we find its value equal to 1,700. To solve for F sub P, the value of sigma K must be determined. This term must be calculated because of the outlet increaser on the valve. The increaser is used in this application to decrease fluid velocity, and therefore acoustic noise, downstream of the valve. The calculated value for sigma K is negative 0.43. F sub P can now be determined, and is found to be 1.08. So the actual value of F sub P C sub V is 1,840. A comparison to the required value shows the installation provides sufficient flow capacity. Now there is an additional consideration that must be made when sizing a valve for gas or vapor applications, and that is the thermodynamic effect that throttling will have on the process fluid. To help explain this effect, let's look at a molar diagram. This is a portion of a molar diagram for steam. Diagrams for other fluids are similar in structure. As you can see, it plots fluid enthalpy against entropy. It's necessary to understand that throttling is an isenthalpic or constant enthalpy process. This means the enthalpy or heat content of the fluid is not changed by throttling. However, it does not mean that fluid temperature remains constant. Let's look at an example where saturated steam at 400 psia passes through a control valve and is reduced to a pressure of 50 psia. The given inlet conditions correspond to this point of 400 psia on the saturation line. Notice that the temperature for this condition is approximately 450 degrees Fahrenheit. Steam at the valve outlet has the same enthalpy as at the inlet, but its pressure is only 50 psia. So this point represents conditions at the valve outlet. Notice that temperature has dropped to about 340 degrees. Most fluids undergo a temperature drop when throttled, although many result in much lower temperatures. For example, when ethylene at 400 psia and 40 degrees Fahrenheit is reduced to atmospheric pressure, its temperature will fall to about -40. This effect is called auto-refrigeration, and many fluids are subject to it. If low temperatures like this occur unexpectedly, problems can develop. Valve and piping materials may not tolerate them, and failure may occur. Also, any water vapor in the fluid may freeze, and if conditions are severe enough, may prevent proper operation of the valve. Other problems associated with this thermodynamic effect are hydrate formation and condensation. Additional material can be found in your text, but for now, stop the tape. In order for a valve to provide the required degree of control, its actuator must be properly selected and sized. Some considerations when selecting an actuator include reliability of operation, simplicity of design, and of course, cost. Now, these three goals are actually interrelated. For example, when actuator cost is being evaluated, there's more to consider than just its purchase price. Maintenance costs, labor, and material must be considered, as well as costs associated with unscheduled process downtime. As you know, these factors are related to the design and reliability of the actuator. Another factor that will influence the decision is whether pneumatic, hydraulic, or electrical power is available. Obviously, the use of an actuator type that does not have a readily available power source may add considerable expense to the installation. After you've identified the power medium available, details of the various actuator styles in that category must be examined. Compare this information to the needs listed on your datasheet to determine the actuator type that will do the job. For example, suppose the initial choice is a pneumatic actuator. Factors such as valve stroke may require the use of a piston actuator or a rolling diaphragm instead of a standard diaphragm actuator. Environmental factors such as temperature and atmospheric contaminants must be considered for their effects on diaphragm materials. Of course, what the actuator response must be on a loss of actuating power, whether pneumatic, electric, or hydraulic, must also be kept in mind. It's also necessary to identify any auxiliary devices that are required. For example, the application may require a manual override that can be provided by a hand wheel or a limit stop to prevent the valve from being opened beyond some predetermined limit, or a positioner to provide the required degree of control. Another auxiliary device is a transducer that converts an electrical control signal to a pneumatic control signal. After evaluating all of this material, a preliminary selection can be made. At this point, it's important to determine if the actuator chosen is compatible with the installation. It must be verified that the actuator is mountable on the valve, and that it will fit into the space provided and allow adequate room for maintenance. Once you're satisfied that the best actuator for the job has been chosen, the actuator can be sized. Generally, the actual sizing calculations will be done by the manufacturer. However, proper sizing still relies on the accuracy and completeness of data that you provide. In order for you to provide the manufacturer with all of the relevant information, it's helpful for you to be aware of all the significant factors involved in actuator sizing. So let's take a look at them. The first of these factors are the static forces that exist while the valve is under pressure, but when no flow exists. The predominant static force in a common globe valve is a result of the pressure unbalance across the valve. As you can see, two forces are applied to the valve plug. Each force is equal to the exposed area multiplied by the pressure acting on that area. The higher the differential pressure, or the larger the exposed area, the greater the unbalance in forces. The direction in which this force acts will depend on the direction of flow through the valve. So you can see, information regarding pressure and direction of flow are critical to actuator sizing. Another static force called stem force is developed here at the end of the stem. It's equal to the area of the stem multiplied by the pressure the end is exposed to. This force must be taken into account separately since there is no opposing force in the valve body. Friction is another static force that must be overcome. For linear action valves, stem packing is one of the major contributors to friction. Information regarding the type of packing to be used is critical, since packing friction can vary by as much as a factor of 5, depending on the material that's used. The valve leakage classification also affects the amount of force the actuator must develop. A lower leakage tolerance may require a much greater actuator force. Rotary valves are also affected by static forces, but in a much different manner. In ball valves, such as this, as well as other symmetrical valves, there is no unbalanced static force that the actuator must overcome. However, the frictional force created between the seat and valve trim is extremely high. With a full ball valve, this friction exists throughout the valve travel and must be considered when sizing an actuator. The seal materials used, as well as the process fluid, can have a great effect on the severity of this friction. In other valves, like a butterfly valve, this friction may only exist when the valve is closed or partially closed. The torque required to overcome this friction is often referred to as breakaway or breakout torque. Additional static forces affecting rotary valves are presented in your text. Now, let's look at what happens to forces as a valve opens and fluid begins to flow. These are the dynamic forces and can be extremely complex. We'll use a graph to illustrate how these forces can vary as valve opening increases. This plot represents the dynamic force on the plug in a quick opening globe valve when flow is tending to open the valve. As you can see, the force varies with the amount of flow through the valve. With the same valve installed so that flow tends to close the valve, the dynamic forces acting on the plug are considerably different. Again, the direction of flow through the valve is important. Of course, the shape of these curves are also affected by valve design. For example, this curve represents the dynamic forces on the plug in a double-ported valve. Clearly, it affects the complexity of actuator sizing. So far, these curves have illustrated the dynamic forces that exist when there is a constant differential pressure across the valve. However, in most applications, differential pressure will decrease as the valve opens. So an actual curve for this valve may appear more like this. A significant difference may exist at the end of the curve. In some installations, as shown here, the force gradient can become negative. If this negative force gradient is unexpected when the actuator is sized, but occurs in the actual installation, valve instability will result at higher flow rates. On the other hand, if it is expected to occur, a stiffer spring can be used to compensate for the problem. Up to this point, we've been discussing steady-state dynamic forces. In addition to these, there are high-frequency buffeting forces caused by fluid turbulence. If not accounted for, these forces can also cause valve instability. So, in addition to having sufficient power to position the valve, an actuator must be stiff enough to resist motion due to buffeting forces. You can see that there are many factors that affect actuator sizing. Complete and accurate information must be provided to the manufacturer to ensure the best actuator size for your application is selected. Stop. So far in this program, you've seen how to select and size control valves that provide optimum performance for an application. But even the ideal valve for an application won't perform as expected if it's not properly installed or maintained. So let's turn our attention to installation and maintenance. When a valve installation is planned, it's important to consider safety first. For example, you should always assume that a leak will occur. Then determine the hazards associated with that leak. Will a corrosive liquid spray onto an electrical wireway? Or will a combustible fluid drip onto a hot pipe? If the answers to questions such as this indicate that hazards will exist, then steps need to be taken to eliminate them. It's also important to consider the design of the installation piping. For example, it should be determined if block valves are necessary. Will vent and drain valves be required to relieve pressure so that the valve can be maintained? Is a bypass valve required for manual operation of the process? Or perhaps an installed spare might be required. The attitude of the control valve also needs to be determined. Every effort should be made to keep the stem oriented vertically. If vertical orientation is not possible, actuator support such as this may be required. If adequate support is not provided, stem misalignment can occur. This can cause packing leakage, flange leakage, or seat leakage. Additionally, hysteresis may also increase. Similar problems are introduced if piping to the valve is misaligned, creating stress on the valve. You should also determine the possibility of foreign objects being present in the process during initial startup. Materials such as weld slag or corrosion particles can ruin the seat or plug in a control valve. If there is a potential for this problem, consider installing screens or strainers upstream of the valve. There are many considerations for valve installations, too many to present all of them here. The manufacturer's instructions and your facility procedures will provide you with additional information regarding proper valve installation. Now, in addition to proper installation, the quality of valve performance relies on the quality of valve maintenance. It's critical that new control valves and actuators become a part of your facility's maintenance program. Manufacturers' instructions often provide the guidelines necessary for establishing the preventive maintenance program for a valve. Requirements for valve repair also need to be evaluated so that needed parts and materials are readily available when an overhaul must be performed. This training program is general in nature. The examples given of equipment operation and applications are for illustration purposes only. Manufacturer's specifications and guidelines, as well as your facility procedures, must be used when sizing or selecting a control valve. Always remember that safety is your responsibility.